Welcome dear friends for another exciting video. Today we are going to learn how to tune a PID controller using Ziegler Nichols method. So in this tutorial we will learn how to obtain process reaction curve to obtain different tuning parameters, and then we will definitely use Ziegler Nichols tuning method to determine the optimum controller tuning parameters. Okay, so let's move the first objective, that is the process reaction curve. There are many different methods to tune the controller, and one of them is to obtain the tuning parameters by drawing a process reaction curve. And how we can obtain this reaction curve from a already existed process. So you just simply have to disconnect the controller and make the control loop in the form of an open loop system, and then in second step we have to introduce a disturbance to the system, and this disturbance usually measured in terms of percentage, and it could be introduced as a either as the set point or the process variable. And these types of the curves are obtained in open loop system when there is no control of the system, allowing the disturbance to be recorded. So from the process reaction curve one can acquire the process gain and the time constant and the dead time, that is alpha. So what is these three parameters? K is the process gain, alpha is also called transportation lag or dead time. So how we can define it? The time taken from the moment the disturbance was introduced to the first sign of the change in the output of the signal. So we will see all these concepts in next slides, where we are going to draw the process reaction curve, and tau is the time for the response to occur. So this is our problem statement that we are going to solve in Aspen HYSYS. So it's just a water filling tank. All the parameters are given, like the feed flow rate, temperature, pressure, and different valves, and there are two control system, two control loop. One is the flow indicator controller and level indicator controller. So our objective is we have to tune LIC controller in this system. So to obtain the process curve for this process, what we have to do, we have to disconnect the LIC controller from the valve 2 to make the loop open, and then we are going to decrease the valve 2 opening by 25%, and then the response of the system will be recorded. Obviously when we decrease the percentage of valve 25%, when we close the valve 25%, obviously the level inside the trunk inside the tank will increase. Okay, and these are the parameters that we have to use when we are going to build the dynamic simulation. So I will discuss it when we are going to build them, and these are the parameters that we are going to tune for LIC controller. And here is the process reaction curve. So this one, at time 0 we just introduce the disturbance into the system by decreasing the percentage valve opening of control valve number 2. Okay, and then the system starts starts to give the response. The first response that we detect, it was after almost 100 seconds, and this orange line is showing the response of the system. So we call it response curve. Okay, so it is called response curve, and this white line is actually the introduction of the disturbance, that is 25%, and the response of the system is almost 24%. So the ultimate change in the value of the output excuse me, is 24%. Okay, so from this response curve we can have the transportation lag value, the process gain value, and the tau, or the time constant for this system. Okay, so what we have to do, we have to take the inflation point of the response curve and then simply draw a tangent line. Okay, and then the tangent line, just draw the vertical line. So the point from where this tangent line crosses the x-axis until this point, where it crosses again x-axis, this vertical line, this time is called time constant. It is called tau, that is required to change almost 63.24% of the total response of the system. Okay, and the time when the disturbance was introduced and the time where the first response was recorded, so this is called dead time or transportation lag, and it is represented by alpha. For this case it is 100 second, and for tau is 480 second, and the gain value we can calculate it via Ziegler Nichols method, and k is can be defined as ultimate change in the value of the output, that is 24%, and the magnitude of the step input that we introduced in the form of disturbance, it was 25%. So the ratio of these two number is the value of k, that is 0.96, and we already know the dead time and the time constant. You just simply have to change or convert dead time and time constant from second to the minutes, and here this table is the representation of the parameters that are fixed for Ziegler Nichols method. So for proportional controller, the Kc value is calculated via this relationship. All these are empirical relationships. So the proportional indicator is equal to this value, and for PID controller you have to introduce these values. So because we are going to tune PID controller, we will calculate the value of Kc, Ti, that is the integral time, and Td is the derivative time, using these numerical relations. Okay, so when we insert all the values, the value of Kc for this system is 6.02, the integral time is 3.32, and the derivative time is 0.83 minute. Okay, so we have calculated the Ziegler Nichols tuning parameters for this system. Here I just want to mention that this response curve is just the arbitrary or just for example. It's not the representation of any real system. To have the real system, you must have the system in operation, and then you just simply apply this method, that is the disconnect the controller from the valve and then record the response as a response of introducing the disturbance in the system. But here it's only for understanding and demonstration. Okay, so there are some advantages of this method as well as some disadvantages. So the first advantage is it's quick, easier, and not a complex method. It is robust and very popular method, and of these techniques, the process reaction method is the easiest and the least disruptive to implement. Okay, and what are the disadvantages of this technique? It depends upon purely proportional measurement. So the value of Ti and Di, they are also dependent on Kc. So actually it is mainly all the values are dependent on proportional measurements. Okay, and the approximations for Kc, Ti, Td values might not be entirely accurate for different systems, and also it does not hold for integral only controller, derivative controller, or proportional derivative controller. Okay, so these are the some advantages and disadvantages of Ziegler Nichols method. Now we are going to Aspen HYSYS to build this flow sheet, and then we will move to the dynamic simulation. Okay, and then we will introduce these sizing values of these two valves and the controllers, and then we will see initially the response of level indicator controller, and after that we will introduce the tuning parameters that we obtain by calculation of Ziegler Nichols method, and then we will see the difference between the response of this level indicator controller at the process gain of 5, and also with the process parameters that we have from Ziegler Nichols method. Okay, so let's move to the Aspen HYSYS software to build this flow sheet. So we are in Aspen HYSYS environment. The first step is we have to specify the components which are going to participate in simulation. So in our case there are two components, water and air. The next step is we have to specify the fluid package or thermodynamic property package for estimation of thermodynamic properties, and for that here we are going to choose Ping Robinson as a property package. Okay, so this is all for the property section or property environment section. So now we are in the simulation environment, so we need 3 control valves. So I am just adding 3 control valves. Okay, and we need one tank as a storage. Okay, and what else? At the moment we need these two, but we need 2 controllers. So one flow indicator controller and one level indicator controller. Okay, so when you do this, then just double click on first valve and change its name. I am saying valve 1, and the input is feed, the outlet is, I'm just saying it's number 1, and for each valve the pressure drop is 1 bar. It's just the assumption I'm just doing this as an example to show you how we can tune the PID controller in Aspen HYSYS. Okay, so after that close this one, go to the valve number, this one, so I say it's 2, the outlet is air, and again go to the parameters and specify the pressure drop 1 bar. Okay, close this one and go to the third valve, and here I say the inlet is 3 and the outlet is water. Okay, and go to again parameters, and delta P across this wall is 1. Okay, so now just connect this vessel with the inputs and output. So the input is 1, the vapor output is 2, and liquid output is 3. Okay, after that close it. Now we have to size these valves. So just double click on valve 1, go to the rating, go to the dynamics and see the pressure flow relation is tick. The valve opening is 50% and the conductance for the first valve, the value is given here, it's 75. The CV value for valve 1 is 75. Okay, I'm just introducing here 75, and rest of the things are fine. Just close it, go to the this second valve, I will say it's valve number 2, and go to the dynamics, and here on 50% opening the conductance value is 55. So just double click, click on here and write 55. Okay, and just check the pressure flow relation is tick. So close this one, and similarly here go to the dynamics and check the total delta P is 1 bar, that is okay. Pressure flow relation is okay, and here I am not specifying the conductance value because we are not going to control this valve. So our control valves are valve 1 and valve 2. Okay, so I'm just going to change the name of this valve, so I will say it's valve number 3. Okay, so when you do that, then go to the feed and just introduce the feed specification. Temperature was 25 degrees C, pressure was 5 bar gauge, and the mass flow rate was 5000 kg. And now go to the compositions, and here the water is 0.9 molar mole fraction and the air is 0.1, and then just click OK. So when you press OK, so you can see that in simulation, in steady state simulation, the process is already converged. Now it's time to introduce these controllers. So double click on this first controller, select the process variable, and the process variable is actually mass flow rate. So I'm just writing here mass flow, and then select from the feed side, and the manipulated variable is valve 1 and the actuator position, and select. Okay, so you can see that the first control valve is integrated into the flow sheet, but here it says that unknown range is for process variable. Go to the parameters. So the action is reverse, that is given in our flow sheet, HYSYS reverse action controller, and the specification for these controllers are also given. The set point is 5000 and the process variable range is 0 to 7000. Okay, so we are going to insert it here. So first just change the controller mode from off to auto and introduce the process variable range 0 to 7000, and the set point is 5000, and change the process gain value as given in this table. So the Kc is 0.5 and integral time is 1 minute for this controller. So I'm just changing it here 0.5 and Ti is 1 minute. Okay, after doing that, just check it is on reverse action. So we completely specify FIC controller. After specifying the FIC controller, just click on faceplate, and the faceplate will be appear on the flow sheet for this controller. Now close this one. Okay, so double click on the second controller, and here the object is the percent liquid level, liquid percent level, select, and the manipulated or the target object, output target object is the valve number 2 and its actuator position. Okay, so when you do that, then again go to the parameters, and here change mode from off to auto, and it says the reverse action. It's not the reverse action. If you see in the given process flow sheet, LIC is the direct action. Okay, so we have to change from reverse to direct action. We have to specify the process variable range from 0 to 100%. It's the level, and the set point is specify 50%. That is okay, and the KC value for this one at the start is 5. So we are just going to introduce here 5, and the rest will remain empty. So when you specify it properly, then you just have to introduce the faceplate. Okay, so now we have the faceplate for both of controller with given specific condition. Now close this one. Okay, now just we have to specify the tank volume. Okay, so for that, go to the dynamics, and in here the process the volume of the tank is given, that is 4 cubic meter. Okay, so we are going to insert 4 cubic meter as a level, and we will insert 0 as a liquid volume percent. Okay, to analyze how or to analyze the behavior of the filling of this tank. Okay, so now I think we already specify all the given parameters. It's time to move from steady state simulation environment to the dynamic. For that, just click on this dynamic tab, and then click on dynamic mode, and then this window will appear, and it's saying that there are some changes that are required to move from steady state to the dynamic. So we say okay, make these changes, and then again analyze again. So there is no problem, finish it, and then again press dynamic mode. Yes, we want to enter in dynamic mode. So now we are in dynamic mode. So to analyze the behavior, we want to introduce the strip charts for these two controller. Okay, so for that, just press on tuning. Okay, so after pressing tuning, go to the strip chart. From strip chart, select set point, process variable, output, then create strip chart. And we don't need the output, we just want to compare the process variable and the set point, then display. Okay, so here we have our first strip chart. Just close all these other windows. I am just going to, so this is the strip chart for level control, for flow controller. And now we have to introduce the second strip chart. Okay, so for that, Again, go to the tuning of LIC controller, go to the strip charts and introduce set point and process variable strip chart, and then simply display and close all other windows. Okay, and put it here so we can have clear visibility. So this strip chart is for level indicator controller that uh, we are going to tune, and this one is for flow indicator controller. So everything is already set for to start this simulation. But before that, go to the integrator, and here the acceleration you should change from 1 to 0.05 to slow down the speed, so you can see and analyze what is actually happening in these strip charts. If you put here 1, the speed will be so high that you will not see any change. Okay, so just close this one. And now, before starting the simulation, check that your both controllers are on auto position, auto, and the set point, and see the process variable. So the set point is 50% and here 5000. Okay, so let's start the simulation. Just press run. So you can see that for the flow indicator controller, the set point and the process variable are exactly matching after some time. But in case of level indicator controller, there is the constant gap between the process variable and the set point. Okay, and this gap is called offset, and it is the characteristic of proportional controller. So because we are just only introducing the value of kc, that is the characteristic parameter for proportional controller. Okay, so for example, if I change the set point from 50 to say 70%, and then let's see the behavior, how it will go. So you can see the set point just immediately go up, but the offset is always constant. There is always a offset. Okay, so how we can remove it? So we have to introduce the integral part and derivative part. Okay, but here for example I'm just putting random number. I'm not putting here Nichols Ziegler method tuning parameter. So I put maybe here for example 1 minute, and for t maybe 2 minutes, and then see how it will affect. And from 70 to I will change it 50% as the level, and then run again. So now you can see the oscillation. Okay, but you can see that the process variable is going down, down, down. And why it is happening? And the system is actually becoming unstable. Why? Because I introduced the great number or high value for TD, for derivative control. So if we increase the number of the time derivative time constant, so the system will become unstable. So you can see that if I run it for further, so the behavior will be very strange. The cycling will continue. Okay, so if we want to improve this behavior, what should I have to do? I just have to decrease the derivative time constant. So for example, I just put 0.5 and then see how the system will behave. Just click run. So you can see now it just touched the process variable and meet, and both are, there is no offset, there is no cycling, and it is perfectly aligned. So this is the way how you can tune controller manually. So this is the manual way to just observe the process response and change these parameters, and then see the response. So if it is okay, if not, then change again. So now let's change again the set point from 50% to maybe 80%, and then see either this behavior stays the same or not. Okay, then click run. So the set point is immediately increased, and this green line is the process variable response, that is going well. It's reach a little oscillate and then simply match the process variable. Okay, so but if I remove the integral term, then what happen? Okay, so I just, now this controller is proportional derivative controller. So now I change the set point from 80% to 50%. Okay, and then run the simulation. So you can see when we remove the integral part, so the offset is again present in the system. So the derivative part only increase the responsiveness of the system. The response of the system is increased due to the derivative term introduction, derivative time constant, but due to the absence of integral time, there is the offset. Okay, and if I remove, for example, if I increase this time more, then let's see what happened. If I increase it 2 and I increase the again set point from 50 to 80% and then run, and now you can see the behavior is almost the same. Okay, so now it's time to introduce here the Nichols Ziegler tuning parameter and see the overall system performance, overall the performance or the response of this level indicator controller. For that, just go to the presentation where we already have calculated these numbers. So for PID controller, we have the KC value is 6.02. Okay, so I am just changing here 6.02, and the integral time constant is 3.32. So it is 3.32, and the derivative time integral, derivative time constant, it is 0.83. Okay, so 0.83. So already the set point is 80%. So we will decrease from 80 to 70%, 10% decrease, and then let's see how the system is going to respond now. So there is one small oscillation. Okay, and then it matched the set point. So I just decrease further 70 to 60%, and then see either the behavior is the same or not. Yes, it's again the same. So just a little oscillation around the set point, and then it's meet to the process variable. Okay, so decrease it from 40 to, I will say, maybe 30%. Okay, and then run. So you can see the behavior. So there is one small oscillation around the set point, and then immediately it meets the process variable. So this is the way how you can tune a PID controller in Aspen HYSYS. So here we tune the PID controller in two different methods. The first one is the manual tuning. So we just changing the KC value, the integral time value and derivative time value randomly, and seeing the response of the overall system, and where it seems behaving well, so we fix those parameters. So this is the simple way of manual tuning. But the other one is the Ziegler Nichols method, that we calculated using the empirical relations of Ziegler Nichols method, and introduce those numbers, and we have a very nice response of the level indicator controller. So I hope you understand, and you like this tutorial. So if you like this tutorial, please don't forget to like, share and subscribe my channel. Thank you very much. Until next video, take care. Bye bye.